Alright, today we're going to look at a pulley system where we've got a block attached to another block with a wire over top of a frictionless pulley. So we'll call it mass 1, mass 2. We'll say there's some friction there. So we've got a coefficient of friction mu, so it's greater than 0. But we'll say the pulley is frictionless and the wires are essentially massless, or say they have negligible mass. We'll never remember how to spell that word. Well, I think that's right, negligible. Basically, the mass of the strings, we're not going to consider them. We'll say that it's so low that they're unimportant. Alright, so first things first, probably what we'd want to know is what's the acceleration of this system. We also might want to know what's the tension in that wire that's connecting them. So, as usual, start with F net equals ma, and we're looking at the entire system. So the whole system includes both masses. So it's the sum of the masses times A. And for F net, you have to think, well, what's doing the pulling? And down is gravity of the second mass is pulling down, but the friction, FF1 over to the left, is opposing our motion. So our F net is Fg2 minus FF1. Now, we can figure out what that friction force is. We know that it's mu times normal force, and we know that block 2's gravity is m2g, so there's an expression for F net. And if we want to isolate for A, we just have to divide by the sum of the masses. And now we have a general expression for acceleration. If we want to find the tension, we actually have to look at each block individually. Doesn't matter which one we choose. We'll start with block 1, and we'll say, looking at block 1, its net force is tension minus friction force, so, because that is basically what is causing the motion and opposing the motion. So you can rearrange that equation to solve for tension. Just have to move friction force to the other side, and now we have a general expression for tension. Alright, for block 2, the tension is opposing the gravitational force that's pulling down, so we say Fg2 minus T. And I noticed later on when I was making this, I made a mistake there. There's a plus sign, that should actually be a minus sign. We'll fix that up later on. So anyway, we're isolating T. You can prove to yourself why that is. Let's try it numerically now. What if we said that the first mass was 5 kilograms and the second mass was 3 kilograms? Let's see if we can figure out the acceleration and tension of this system. So, the nice thing about doing that generally to begin with is that now we can just plug in the values that we have, and we need to also create a coefficient of friction. So let's say we knew it was 0.20. So we plug everything in. Notice on the bottom, 5 plus 3 is 8. I'm going to grab the calculator. We can do this all at once. Basically, you've got a net force on the top of the fraction, and you're dividing by the sum of the masses, the bottom of the fraction. Right, turns out you get an acceleration of 2.45. That would be in meters per second squared. And we'll round it with sig figs to around 2.5. In terms of the direction, the block 1 travels to the right, block 2 travels downwards, so we can show that with a little arrow there. Alright, as for the tension, if we look at it as block 1, we plug in our values. Block 1 was 5 kilograms, and it turns out we get a tension of, I'm going to do this off to the side, my handheld calculator, it's about 22 newtons. We can check, and here's where I noticed I made a mistake, that plus was supposed to be a minus. Maybe convince yourself on your own piece of paper why that's a minus sign. As you rearrange for T, notice you have to subtract M2A to the other side. Anyway, if we're doing this right, we should get a tension of 22, the same as we did from block 1, because it's actually the same wire that's connecting the two masses. And sure enough, it does work out. You get the exact same tension, and we're done. We've got the acceleration, we've got the tension, that's all we wanted.